Okay, perfect. It's not increasing. Aha, perfect. And if this is on, then we are chilling. Better? Nice. Okay. So, welcome. As I already mentioned, we're covering RNNs and LSTMs today. Can I get a quick show of hands for those of you who have either heard of these, know what they are, think you might have some sort of idea? Yeah, I know you know. Yeah. As well.
I know the first one. I know this.
Perfect. And back there, a bit of a heard of it. Heard of it. Okay, perfect. You don't need to know anything. We're going to do our best to break it down in a way that's semi-understandable. This is decently advanced as far as neural models end up going, but in practice, it shouldn't be very difficult to get the gist across. So that's our main goal. Oh, come on. Oh, I know what I did. I didn't click in. Perfect. So we'll do this. All right. So as a recap, because this is the basis for every neural model that we have and every one that you're ever going to see, it's built off of what's, oh my God, is this going to work at all? Oh no, it's plugged in. Can someone take care of this while I do that? Perfect. So the basis of what we're doing is always built off of feed-forward loops. So you have an input, you work towards the output, you learn by backpropagation. Next week is perfect. So in a feed-forward neural network, information is both one direction. So as we already mentioned, input to output, and has hidden layers in the middle where there's values you do not know how to represent. It's in theory a black box. You know what's going in, you know what's coming out, even if it's in the bottom. Nice. And there are no cycles or loops in the network. It's a feed forward. So one direction. This is what we already know. We've already done this. Okay. Perfect. So as for a recurrent neural network, it does some things pretty interestingly that a normal feed forward network can't do. It's just because of how it's designed. So the first really cool thing it can do is that it can handle sequential data. So for example, I mentioned this last week, for those of you who remember, you can use this to do signal processing stuff. So if you have time series data or data that the order of which it's seen matters. So if you have a segment of audio that lasts for a second and you sample every 1/30th of a second, for example, that data can therefore be passed into this and it'll be able to analyze it over time. So sequential data, data that matters the order in which it appears. And it can also consider current input and previously received input. So that's the really, really cool bit about this, is that it can learn the representation of previous values of the thing. And as we look at an example of a long short-term memory block, which we'll get into later today, don't worry, we'll be able to see how it can actually learn and internally represent this type of information, which is pretty, and that's why it's so powerful. Cool. Any questions so far about this? We'll get into like actual concrete explanations of why and how this stuff works as we go along, but as a general overview, this is what it does and how it does it. Feeling good? Yeah.
So I understand that it loops onto itself, but let's say you have a normal neural network, before a neural network, doesn't it still remember the weights if you're putting in data sequentially, right? Or is there something special about?
So it's not remembering, it's not a question of remembering weights. The network still remembers the weights. Those are intrinsic to how it does the calculations. What it can do is remember input. So it knows what you gave it before and can use that to make next decisions. So it has a memory. Instead of being stateless, it has state. So based off of we'll cover a couple of examples going forward, but for example, you give it a sentence, it'll be able to remember some of the words that came before and help it incorporate that into the decision of what should come next, which is what we're doing today, if that wasn't clear, but that's a very common use. So some very cool things this can have is multiple different types of output. We'll cover these in a moment. It does not need to only give out one value or a series of values. It can be very, very flexible. There's multiple different types of recurrence. It can also, in theory, run infinitely long. It just takes a lot of memory. And the really, really cool bit, actually, is that it uses the same weights for every single computation. So you have basically, if we go back one slide, I'll just go click here because it's going opposite pane. As you can see here, it loops. So this function here is just the operation on itself, and it spits an output, and then this output goes back in. And so more or less, in terms of representation, what you do is you just plug in the data over time into the same network. And that changes the predictions because it remembers what it had before. So the really cool bit is that it's not learning how to represent all of it at once. It's learning how to represent it based off of old things that it's already seen. And that's pretty neat, I think. Nice, okay. We good so far? Thumbs up, sideways down? Okay, cool. This is a bit confusing, I'm aware, but we'll cover examples that'll make it a bit more concrete. So, in terms of types of output, there's quite a few. These are the main types of outputs for neural networks or functions in general that we really want to consider. But a recurrent neural network can do a few of these very, very well. The first one that you're probably very familiar with already is many-to-one. So, for example, in a feed-forward neural network, you give it a bunch of different types of input, like height, weight, shoe size, whatever, and you ask it to predict income. But I don't want to keep doing this example, but this is the one that keeps coming to my brain, so we're going to go with it. And you ask it to predict income, and that is going to give you a single output. It can be floating point, it can be Boolean, it doesn't really matter. It's getting one output. So for something like sentiment classification, this is the use that you use it for. So you give it a bunch of text, it analyzes that text and spits out a prediction on the tone of the reader, if they're happy or sad or whatever. So there's a single output. For one-to-many, what you can do is give it an image, and it'll caption that image automatically. This is decently advanced stuff. So like the exact architecture for how it works, I can't really give you guys a great example, but more or less, you train it on a whole bunch of data to optimize the weights, like a bunch of images of like a cat in an image doing a bunch of stuff, maybe chasing a butterfly, doesn't matter. And then it learns the representations of those things in the image based off of like adjusting the descriptions that it has already in the data to what the image represents. And it learns things about that image by looking at them. And so what it's able to do then is make semi-accurate predictions of what the image should be captioned. So it can learn how to represent images as text, which isn't, this was one of the earlier models to do this stuff. So it's very, very powerful. And then many-to-many prediction, lots of input to lots of output. So something like machine translation, this can be used for, it's not very effective, but it can be used for machine translation. It can do video classification. So similar to image classification, you're able to take a video and ask it to explain what's happening in the video. It does not do it very well because the memory that it has is very small, but these are generally the types of output that this type of stuff can do, semi to very effective. Yeah.
Wait, how is image capturing one to many? Because aren't there like a lot of pixels?
So yeah, you can argue that. For the sake of argument, you consider the image to be monolithic because like, yeah, there's a bunch of pixels, but you're not going to take that pixel out of context. So by providing it all kind of in one step into the network, I don't know. I didn't write this example. There are other one-to-many outputs, but this is like a pretty common one that people consider. And you're right, it's a little weird that it's not considered like many-to-many, but yeah. Anyone else? Feeling good? Feeling fly about the types of outputs we got? Okay, so this more or less is how we end up calculating the new output. So what we do is we take the current hidden state of the function, and the input to the function at the current time step, and we pass it into the weights. So like the function that now evaluates what we're doing, this is very oversimplified, but more or less this is what it does. So for every past hidden state, we update it with the new inputs times whatever weights that are present for every step in the network, and we spit out the new hidden state. And that new hidden state is used in the next step and every other step after that to influence the decisions. If you guys think about this, what it means is that every prior step to some small degree is incorporated in making future decisions. So if, for example, you have a paragraph of text and you want to predict the next paragraph of text, you can look at each word based off of those predictions, calculate relevant predictions, and over time it'll, of course, shrink it. But every word in that paragraph will in some small part be incorporated into this within bit precision. Yeah.
You're taking a look at everything previous. It's just
So you're very right, but the way that the hidden state is represented, we'll talk about why that's the problem in a second. The way that the hidden state is represented is a function modifying the hidden state with the input. So because you're incorporating the prior hidden state and the input into the next step, it's already incorporated. Yeah, that's it. Like, so if we look at this equation, right?
Markov.
Yeah, it's a Markov process. That's the very, very simple way to explain how it works. Yeah, so because we're not going to need to keep track of everything, we're modifying it to some now new black box value. we're able to iteratively make decisions off of the prior hidden state. Because the prior hidden state is modified with the prior steps data, we can keep going backwards. Yeah,
So let's just say it's linear, right?
Sure.
So with the previous one, well, like the first one, let's say the first one is like the input's like 0.5,
Mhm.
then the weight is like 2. So then you get 1.
Yeah.
And then so then the previous hidden state would be 1. And then right? Or like so we go, okay, what I'm trying to say is the previous state different than like the current weight? Or like,
yeah, weights are different. The state is just a representation of the functions. So more or less, again, this is confusing and we'll talk about it's in a bit more concrete detail in a bit. But what we're doing is just combining like from step 0 here. We start with some initial state. We have our input at time step 1, and we combine everything, including our weights, with all that information to get the next hidden state for time step 1. And so for every new bit of data that we give it, it's going to learn a new hidden state.
In a slightly different way with a bit of an example, or is that coming in?
There's plenty of examples. All right, this is confusing, like, don't feel lost, feel helpless, I guess. There's a bunch of information, yeah.
So what is the hidden state? That was that.
So think of the hidden state like the value at a node within a feed-forward neural network. It's a value that you do not know, it's a black box. But what that value is used for is to encode the state of the network for future outputs.
is it like a floating point number or is it a?
Yeah, it could be a series. It doesn't really matter for this particular example, but I think generally speaking, it's still is like a really big array. Because it's by weight. So as far as I'm aware, it would be an array. Yeah.
So it's weights.
Yeah, I might have to look this up. I'm not super concrete on this. This is not the type of data that I tend to work with. I work mostly in image space, but yeah, no, it seems right.
Have you worked with any videos?
With video, I mean, that's out of the scope. I can talk about myself later. We're doing this. Kevin, do you want to add anything that I might have overlooked?
Yeah, just a quick little reiteration in a slightly different way that might make more sense. Let's say X1, X2, and X3 are words. It's the dog jumped. The first thing the model is going to do is it's going to take in the starting state of the network. It's going to pass in the, and it's going to get a new state of the network. The network is going to change after it passes in the, right? And then it's going to take that new state from the, and it's going to pass in the word dog, and that's going to change it a little bit, considering the previous state of the network. And it's going to create a new state. This new state is going to be passed in along with the word jumped, previous state along with jump, and create a new step over and over and over until you get your final state of the network. Does that make sense?
So question first.
How do you get then is it the output of the network is the state?
Yeah.
Is it also where do you actually get your like final output when you like so?
We're going to talk about that. There's an example later in the slides, but for now, for that question, we'll answer.
Kind of built on it. So the dog jumped. Is that what like is the training data that was given? You just like creates those or like creates those words naturally. Where like how would one find it?
Well, that would be like, let's say you're trying to predict a new word. That would be like X1, X2, and X3 that it's trying to predict from.
Yeah, so that's your input data.
Yeah.
Okay, perfect. So generally speaking, there is a big problem with this. We're talking about this in theory instead of in practice, but there is a very large problem that we're probably overlooking in this process. Can anyone potentially see it? And I'll give you a hint. It has to do with the fact that we are in fact building off of the old values here. We're going to run into a, yeah.
I think it's like the old values can just like go, like the representation can get like overwritten over time if you run it too long.
That's just a question of memory. So that is technically a problem, but it's not actually, that's by design. Yeah.
Well, wouldn't the problem be that, how do I say this? Basically, like sometimes when you're working with words, you need more words for more context and that can vary depending on the number of words you give it, right?
Yeah, that's just a structural problem. I mean, specifically about implementation. And it's, again, to do with how the values are stored here. We're using one set of weights. And I don't think why this is a problem. Yeah.
Is it, I forgot what it's called, but it's like when like weights like run away or something?
Yes, it's the exploding gradient problem. We've talked about the vanishing gradient problem. This is the opposite problem. So because, let's imagine for a second that we have a weight value of 2. 2 to the first is 2, 2 to the 10th is, what's 2 to the 10th? My brain's gone real smooth, guys. It's 1024. And then 2 to 100 is value in the octillions, if I remember correctly. It might be around 1 octillion, which isn't particularly useful. And so if you have a network that's 100 bits long, you're going to run into a lot of issues, values that are way bigger than the integer limit, and something that is way beyond the scope of actually being useful. So we really want to keep these values manageable, because otherwise this entire architecture is useless. It's just going to explode and make it completely non-learnable. So the solution that was invented to fix this, there's basically 2 of them. Basically, what you want to do is gradient clipping, which just means you want to limit the maximum size the gradient can be. So keep it fractional or very, very close to a low value. Or use a bounded activation function like sigmoid. And sigmoid, if you guys remember, is bounded between 0 and 1. Another very popular option is using 10h, which is bounded between -1 and 1. And this prevents it from ballooning because all your values are kept close to 0 and fractional values can't really get super big. But then we can have the opposite problem. Again, the vanishing gradient. If our values are all really low, then what might end up happening is because we're multiplying fractional values on top of each other, we're approaching the limit of our precision. So if we use like 32-bit floating point, we can get up to like, I think like a few 10 millionths, and then it zeroes out because there isn't enough precision to represent the number. And that's not very useful. And so what we tend to do with that is we can initialize the weights to some value that is a bit more manageable. We can use what's called light activation functions, or use something called long short-term memory, which is, if you guys look at that, the LSTM. This helps us keep some context, and this is the main solution that's used to remedy the issues associated with RNNs. And we'll talk about how that works in a second. Is everyone feeling good so far about the exploding and vanishing gradient problems? We've mentioned the vanishing gradient a little bit before. Exploding gradient we haven't mentioned at all. Yeah.
I forgot, why is it called the gradient problem when it's like the weights that are?
It's the process of gradient descent. So because oh, that's actually a question. Why is it called? It's to do with gradient descent, and the fact that the change in the function is going to be very, very small, as far as I'm aware, or it could just be the general slope of the function. Am I right about that? Or?
Yeah, it's essentially because the way you train the weights in any neural network is with gradient descent,
Yeah.
and the gradient is the slope at that. If you guys remember that 3-dimensional graph, and we had like, oh, it's going to go this way because this is the slope of the graph. That vector that points the direction is called a gradient. That's the definition of that type of vector. And so when that vector gets too small, it vanishes.
Yeah, it's to do with precision, because we don't have infinite precision values for our computers. Like we work in the space of ones and zeros. We are not limited to actual decimal points. And we're limited in the amount of precision we can have on that. So if we go up to like 64 bits, 30 bits, it doesn't really matter. At some point, you cannot go smaller and it zeroes out. And so because we're working in the constraint space of binary values, we need to limit that. But yeah, that's more or less fine. Okay, how are we feeling? Thumbs up, sideways, middle. I'm expecting mostly thumbs sideways. But we'll get to like actual explanations for how LSTMs work and RNNs in general a little bit.
When does the vanishing gradient problem happen for?
So small bounded weights. What that means more or less is if your weights are fractional and you keep multiplying them on top of each other forever, you're going to run into really, really small weights. So think of the fact if you raise 1/2 squared, you're going to get 1/4. 1/2 to the 10th, you're going to get 1024. And then 1/2 to 100, you're going to get.
When you mean to 100, you mean because it's like recurring on itself
Yep.
100 times potentially?
Yeah, you're going to have like 1 octillionth, which isn't a particularly useful value.
It's also because if you go back to the picture with like the weights, you could see that the same weights were going to every iteration.
Yep.
So let's say you're passing 20 words through, and each of those is a step. That means that single weight is going to be raised to the 20th. So if the weight is less than 1, it's going to get really small really quick. And if it's greater than 1, it's going to get really big really quick. And so that's why it's hard to find this balance between, exploding versus vanishing gradient.
Yeah. And the solution, generally speaking, it's called long short-term memory, which we're actually about to talk about. So long-term dependencies. Let's think about this in the context of English. So, quickly, if you were given the sentence, the clouds are in the blank, how would you finish the sentence? What word would you put there? Sky. Beautiful. The clouds are indeed in the sky. They are not on the ground or in a volcano. Excellent. So tacos are my favorite. And then blank food is the best. What word would you put in the blank?
Mexican.
Beautiful. Mexican food is the best. That's very true. I lived in France for 10 years. I can speak fluent blank. Quick question. The answer is actually Flemish. I'm kidding. It's French. Okay, perfect. Yeah, so you guys get the idea. It's not that complicated. But more or less, the idea of a long-term dependency is that you have different parts of context that are included further away in the sentence. So for something like clouds are in the sky, you know that it's like pretty just by know what clouds are and where they should be in theory. Tacos give us context to a type of cuisine, and the country in France gives us the context to the language French. Because of those associations already within the sentence, we can build a model of the space and say, oh, well, if I'm in France, I'm probably speaking French because that's the language people speak in France. And if I'm having tacos, it's Mexican food. And so what that means is we should, in theory, be able to predict additional words in the sequence of context. So because we have information already available in here somewhere that we know that it's likely associated between this and this, like we do with our own brains, we can therefore probably predict new words that we haven't seen with this built-in context. And as an additional note, what can end up happening is that there is a very big separation between them. So for example, you have something with 3 sentences, that's going to be around like 30 words in an average case. Trying to remember a dependency 30 words on can take up a lot of memory. And like we already talked about with the initial representation, we're going to be raising the same weight to itself 30 times. So there's going to be a pretty big potential for wiping out. So what we need to do is find a way to maintain this context over long periods of time. And this is where the idea of long short-term memory is. Yeah.
What is the dependency?
A dependency just means like information that relies on some other. So if you know this, you are more likely to know this. And so this is the idea of, again, the long short-term memory. The long means the long-term dependency. The short means the time that the memory is. Okay, let's keep going. So quickly fill in the blank again. Jesse's such a good salesman that he continues to get returning customers as well as new ones. Blank was awarded Employee of the Month.
Jesse.
Yeah, it should be Jesse, right? Like, that makes sense to your brain, but for a computer, there's like, I don't know, 15 words in the way. That's not particularly easy to remember, and it takes a lot of memory in order to keep all of this in place. So we need to have a way to effectively manage and relate them to one another. And if you didn't have additional context, saying Catherine, for example, might make a bit of sense because you have no idea what came before, and it was pretty far away. But this is the idea behind long short-term memories. And generally, this is a 3-step process. This is the general block diagram for a single long short-term memory node, and we're going to walk through this. It looks scary. It kind of is, but we're going to do our best, and it should be somewhat understandable by the end of it. And we're going to talk about how it works in general. But it's generally a 3-step process. The first thing that we want to do is forget irrelevant aspects of the previous state. So if, for example, we don't really need to know some bit of information that already exists there that isn't going to be adding new information to what we already have, we can probably get rid of it. The next thing we want to do is update the cell values. So that'll be somewhere around the middle here. We'll talk about this in a bit of detail. We're going to change the weights of the network. And then we're going to decide what part of the current state makes the output. So we're going to do calculations and decide probabilistically what is going to make us have an output. And I'm going to hold questions before I ask them for a little bit because we're going to talk about this in a bit of detail and then have a recap. So we'll have time for questions. Okay, perfect. So step 1, we're at the input of the network. Okay, perfect. So the first step in the network, we want to look at the previous state and the current input xt. So this is the recurrence formula, basically. What this cell represents is the relationship between those two. So let's say the previous state is that, so ht minus 1 in this case, node number 2, Walter is good in chemistry, which is, not super related. There's nothing about these that are similar at all. Point 3, so this is our current input, is that Jesse's a great salesman. Yesterday, he mentioned that he always gets repeat customers. What do you want to forget in this context? So what information isn't particularly useful to us that really won't help us make better predictions? Any thoughts? Yeah,
Well, you just need to remember maybe like great salesmen.
Yeah.
A specific example of like customers.
yeah. Basically, what we need is to remember who's a great salesman, that they're a great salesman. And yeah, that's more or less it. We don't really need to remember anything about the fact that Walter's good in chemistry. So our previous state isn't particularly useful for us. And this is an oversimplification. The hidden state is not going to look like a string of tens. But instead it's going to look like more or less just a bunch of numbers. But generally speaking, yeah, we want to just remember things that are going to be relevant to our future predictions. We're going to keep going. The next thing is in the middle of this network here. We're going to just do additional calculations and new combinations. So the first thing that we need is a sigmoid layer. So we need to consider which parts make it to the output. This is done probabilistically. So for you guys that remember or don't remember, sigmoid, it's just kind of like a squiggle that's bounded between 0 and 1. And the neat bit is that we can plug values into that equation and it'll spit a value out greater than or less than 50%. And we can score this based off of how likely it is. That'll allow us to get closer to a prediction that'll make sense. The tanh layer, this hyperbolic tangent, if you guys want to look up the equation, how it looks basically the same as sigmoid. It basically adds weight to the values that are being passed on their importance. So because this is bounded between -1 and 1, we can actually give it a positive or negative value pretty easily, as well as an additional fractional multiplication value. And then we do an input gate to determine which information is let through based on significance. So what we're doing here, I think this line down here is for the input value. So we walk up here. This is a combination of the previous hidden state and the input. So we walk up here in step 1, combine these with some sigma. I think it's just our sigmoid activation, and then we do, I think, a dot product. That's step 1. Step 2, we go over here. We take our input and we do 2 modifications to it. First, we pass it through sigmoid, and then we also pass it through tanh. We do a linear combination dot product of them, and then we sum it up to the values that were calculated in step 1. Good? Yeah.
So you do sigmoid.
Yep.
Times the weight.
Yep. Or the hidden state. Yeah. The
Oh, the
hidden
hidden
state.
state. Sigmoid times the hidden state.
Yep.
Plus sigmoid times the hidden state plus tanh.
So what we do, okay, this is confusing. We'll walk through it now. So in step 1, what we do is we modify the input data with sigmoid and multiply it against the hidden state. We combine them, right?
Wait, is the top line the hidden state or is the bottom line?
This line represents the hidden state. This line represents the input.
Oh, you add it to the hidden.
Yeah, yeah. I don't know what this one is. I'm pretty sure there's the weights. So you do a combination of the weights and the input. And you add it to the hidden
Why
state.
did they label the fucking inputs and outputs?
Yeah, you know what? That's super convenient. But this is, so we'll get to this in a second. This is output. This is the new hidden state, and this is. I actually don't know. I think I might forget. I don't remember this diagram very well. The older versions of the slides actually had the inputs labeled, so I don't know what happened to them. But it's fine. So then in this layer, we do modifications again to the combined weights and input values, combine them again, add it to the new hidden state that's up at the top there and do more funny calculations.
But the X means a linear layer, so if you do sigmoid.
X is linear
The X mean like a multiplication?
multiplication. It's a linear combination. So we're just doing, I'm pretty sure it's a dot product.
But.
And then here it's summed, it's the same dimensionality. Just add them up. Yeah.
How are you like determining significance?
It's to do with the probability that's predicted here. It's a question of how the data is actually modified. So if, for example, your data is represented as a vector, which you would need to do to have any sort of relationships, you can't really predict based off of words alone. So there needs to be some sort of numeric representation for them. Either you store it as a vector of likelihoods or in some sort of actual vector representation of the data. You then take that and you multiply it by the weights as well. And this would be easy.
Weights to determine the importance?
Yeah, it's typically what it is. Yeah, the weights determine the importance of each step within there, and you do combinations with higher steps. Yeah, okay, confusing. Diagram would help with having additional labels, but our purposes, I think. Step 3 is the end where we actually make our predictions. So what we first do is we decide what part of our current cell state make it to the output, which is, I think, done here. No, that's output there. So yeah, we take, again, sigmoid layer decide what part of the cell state make it to the output, very redundant. So we take our input, pass through sigmoid, multiply it by our current hidden state after it's passed through the 10H layer. And that decides. Whoa, wait, how is this organized? Sorry, guys. Yeah, pass through 10H combined seemingly with another dot product. And then passed out as output, the new hidden state. And actually, the new hidden state is already persisting up here, it looks like.
I just looked up.
Oh, please, yeah, please give me context.
Okay, so just a couple quick clarifications. I'm gonna go back a little bit. So the first thing that happens is this step actually figures out what to forget. This is like, hey, what if the input? So let me back up a little bit. This is the memory. This is the long-term memory. This is, if you guys remember earlier, this line up here is what the previous state of the network is. If you guys remember back when we were covering RNNs, like half an hour ago, it was like, oh, remember the memory change updates its states, yada, yada, yada. Do you guys remember that? Yes? Okay, cool. This bottom line down here, this is the output. So the output gets sent out to the user, right? But it also gets passed forward. And therefore the output of the previous one gets passed in here. This input is the actual, like the input we're getting currently. So again, long-term memory of the network itself. This is just the immediate previous output, the immediate next output, and then also the immediate next output. So this bit is like, hey, given our input, given the previous output, what should we be forgetting from our long-term memory? What should we be getting rid of? Then we have, oh, okay, so new stuff, what should we be adding to our long-term memory? This does CAN-H, as we said, to look at how much to value each part. So this is, hey, what parts of our input combined with our previous output? So these are combined. What parts of these do we want to include? And then also, how much do we want to weigh each part? So let's say we have Jesse is a good salesman. We know we want to include that. That's what this decides. CAN-H says Jesse and salesman are really good. Those are things to really remember, and great is also good to remember. And then we can remember that, you know, for correlation, but it's not important. This decides of what we remember, how important is each little bit. And then this sends it to the long-term memory. This updates the network and says, hey, this is the new information, keep this in memory. And then we take the inputs over here. So yeah, that's all explained there. And then we take the inputs over here, and we again pass it through here. This should actually have an arrow. This isn't going back up. This is just pulling down. It's just pulling down information from the long-term memory to create the new output. So it's taking our input and our long-term memory, and it's creating a new output, sending it out to user, and also sending it to the next block. So this part, it's done updating the model. The model's been updated, and we're just generating the new output. So again, what should we forget from the model? What are we going to update the model with? And then finally, let's generate our new output. Does that make sense? Can I get some thumbs up, thumbs to the side, and thumbs down? Yeah, what's up?
So makes sense, thank you. Jesse, a good salesman, like how does the program understand that those two have a strong
It
relationship?
learns it. It's weights that are in. So neural networks, machine learning, training, all of that stuff. This is applied here. This is that step of exactly how to get that place.
I get the steps.
Right.
I just don't really understand what's the point of all these sigmoids and features.
So the sigmoids decide what to include in each of these steps. The sigmoid says, oh, this value is important for this. Otherwise, you just always have the whole input going in, and it would first take the whole input. Oh, forget all this stuff in the first step. Oh, take the whole input, add the whole thing to long-term memory, and then finally, oh, take the whole input and generate the next output from that. That defeats the whole purpose of long-term memory, because then we're just back at RNNs where everything's equally as important. Does that make sense?
So
sigmoid decides what to include from the input, and then canput does something similar, but it decides how much importance to put on each thing that's included. Yeah, what's up?
Does sigmoid represent like a neural network with a sigmoid activation, or does it
No.
represent
I got it.
literally a sigmoid function?
Okay,
by
okay.
itself?
So it's the sigmoid function. So what this means, more or less, we're just gonna look at the functions because this will actually help explain it. What the sigmoid does in this case is it scales the values between 0 and 1. So if it's 1, it's like, I don't, what is that? It's just probably, it should be in.
Yeah.
Like, it makes sense so that it should be. It's really, really high probability, close to 1. Very, very likely. If it's close to 0, it sucks. Get rid of it, we don't need it. It's not important to remember. The tan H represents the statistical importance. So if it's negative, it's probably not very important. If it's 1, it's very important. So a very, very good thing to remember, we have high value on the sigmoid and high value on the tan H. And so this operation here, where we did the dot between those two vectors, gives, or just the multiplication between the vectors, actually don't even need the dot. It gives us the value we want to remember. Yeah.
So why do we need a sigmoid and attention? Why can't we just run like a lot of sigmoids with attention? And it's like, why do we need to?
That's a great question. It's because of the sign. So because we can represent like with a positive or negative a lot better than between a 0 and a 1, we're able to represent a more diverse range of values.
I see, so can't we just always run the tangents as opposed to having sigmoids?
Negative times negative will give us a positive value, and it's not disturbing. The importance is that we only have one negative. All right, cool. Huge headache, but yeah,
Where are the weights in this?
the weights.
The weights are part of
Yeah,
the,
these operations here, right? These combinations and
Do they use all the same weights?
well, yes, so if you remember back, if we go back just real quick to all the way RNNs with, all the way back at the beginning, the weights are always the same, they're passed in through here, and then they're updated after everything's gone through. So if you guys think about neural network training, we're updating the weights each epoch. One epoch would be going through the entire thing. So this is one chunk of an epoch. Think of this not as a network, but as a node. So do you update the weights every time you put information through a node in a neural network? No, you do it at the very end. So the weights are always the same, and the weights are part of the model that we're kind of, using here. If that makes sense.
yeah. Confusing as hell.
Do you multiply, do you use the nonlinear function before you multiply by the weights, or do you multiply the weights over?
It's a part of the combination. So like here, what we're doing is we're combining the hidden state of the input, and then we're passing it into the sigma, plus and minus. So the actual combinations before we do 6 and before we do 10 inches. The weights are always incorporated like as kind of the hidden state, I think is what the weights are technically the
Yes.
representation. Yeah, so the hidden state is the vector. Yeah.
The hidden state is the one here.
It's the one at the top.
Yeah, no, that's the map. The hidden state's down.
Oh, yes, yeah.
So the neural, where's the actual like neural network applied? I guess before all the sigmoid functions.
Typically after, if anything. So it's really cool. You a lot of the time don't actually need a feed-forward neural network for this. What you need is basically a way to translate output vector into a piece of data. So a project that I've done recently, just for fun on my own, not for prep or anything, just like a project that I wanted to do, I wanted to do a little bit of stock market prediction. So what I did is I got all of the historic data given for one specific stock. I trained a long short-term memory model on the first 80% of it, and I asked it to predict. And so what you have to do in order to make it usable, discernible data is you need to take the output from the long short-term memory model and pass it into a single feed-forward layer to give you a value between 0 and 1. So just a single sigmoid activation, converting the vector of the output into some sort of physical prediction. But a lot of the time, it's not necessary, or there are other ways to do that.
Would it be wrong to think of the nonlinear functions as a type of normalization function?
Yeah, the normalization. They normalize between 0 and 1. That's the point. Or -1. Okay. Lots of questions. I don't blame you guys. This stuff is hard. But yeah, this is generally the idea of it. So we analyze the previous step to see if we can forget anything. We use sigmoid to pick up important parts of the input and 10H to assign statistical significance to the values. 1 sec. And then we control the output by applying sigmoid and normalizing it using 10H. Yeah.
So the memory, that is specific only to LSTMs and not part of RNNs.
Yep. Yeah.
And are memories also usually depicted the same way as the hidden state? Would it usually be like a bunch of an array of
It should be. I mean, you could look at the doc. I'd suggest looking at something. This is not something I have subject matter expertise with. Subject matter expertise with. I have the medium-ish understanding of this. I could spend maybe an hour or two really looking at the math and give you a concrete answer, or even like 20 minutes, but I just don't know that. off the top.
Yeah, so when you use the LSTM, you just use like a library LSTM or something.
Generally, no one programs their neural networks from scratch. It's much faster to just. Yeah. Okay, cool. We feel funky fresh, brains rotted from the math, because I am as well. And we're gonna do some code now, I think. Oh, never mind, perfect. And so in theory, after doing this process, it should predict this. But like, that was kind of common sense. I was thinking about it, like it's talking about the one person. So after doing all these operations, in theory, what the model should spit out is a semi-accurate prediction of who actually should get employee of the month based off of their record as a salesman. Okay, perfect. Time to code. You guys have your funny laptops, here's what we're gonna do. We're gonna go to tinyurl.com/sky-rnn-lstm. We had an earlier link, for some reason it's broken. It should be open already. Oh, maybe. Oh, let me freeze this for you guys. Oh, that's good. Hold this. Cute. Okay, dope. Okay, now I'm also going to end the recording on Zoom because we figured it out. Bye, guys.